Okay, so there's a lot of stuff, guys. There's a lot of stuff that we could talk about with the ellipses and hyperbolas and parabolas and really all the physics behind them and how useful they are to us. And like, parabolas are useful in like microphone systems, and hyperbolas are useful in telescopes. And we can talk about how we use them in real life, but we do not right now have the time to do that. Okay. So what I want you to know is that they are useful. They're used all the time in physics classes and the construction of instruments. Okay, very high-powered telescopes and stuff like that have hyperbolic lenses. Okay, relationships between the lenses are hyperbolic. If you've ever watched like an NFL football game or a baseball game or whatever, and you see like the reporters on the sideline, these people always get knocked down because they have like these big saucer dishes, and they're clear, and they got these like yellow or orange vests on, but they can't move these things out of the way, and people always drill them, and I watch it, and I'm like, they never help each other out. Like, I'm an NFL player, and I hit this late. I saw it on the Buckeyes game today, and actually the guy helped the lady up. At the end of the Buckeyes got in that little scuffle. Somebody, this is the first time I've ever seen it. Somebody actually knocked over a person on the sideline and wouldn't help them. They hold these dishes. Those dishes, the curves on those are parabolic, okay? Because the sound waves will bounce off that parabolic dish, and then they get redirected to a focus where the microphone is. Does that make sense? And so that it allows you to concentrate sound and other waves, whatever other waves you want to kind of concentrate on, basically a microphone or an antenna or something to enhance sound or enhance some type of other signal. Okay, so that's the use of parabolas. We're not going to talk too much about parabolas, if at all, because of how much we've talked about them already. But there is a conic section way of talking about parabolas, equation-wise, algebraic-wise. But in all the math classes that I've taken, which is probably a lot more than a lot of you will take, okay, I've never had to use the conic section form of a parabola. Okay, it's really not that beneficial in regards to other courses. Okay, now you may every once in a while need it or use it, but they're very far and few in between. Just kind of give you a visual of what we're talking about here. Remember conic sections. What we do with conic sections is that we take two cones and we invert them on one another. Okay, so our green shapes over here, two cones inverted on the vertex, right? Okay, and then we take a plane, okay, and we slide that plane through the two cones, and the cross section of the plane and the cones is what we'll record as a conic section. Does that make sense? Okay, that's why it's called a section. It's a cross section. Now, the angle that we're interested in here, or the angles that kind of dictate what conic we're getting, is the angle, you can kind of look over here at this image here. It's the angle of the plane, its intersection, okay, with the vertical axis. So imagine a vertical axis going through kind of the, let's see if I can get the plane out of here real quick. Okay, think about a vertical axis going through the vertex of the cones, straight up and down. Is that doable? Something you guys can visualize? All right. So the angle of that vertical axis with the plane, okay, so here's our plane over here, just a two-dimensional rendering. Here's our plane. There's the vertical axis. That angle right there, that's created, okay? And then this angle right here, which is essentially just half of the vertex angle, okay? The relationship between those two angles dictates what type of conic section we get, okay? So we can see here that if I put my plane in, let's just make it real easy. Let's make this beta go to 90, okay? And right now, so what we're seeing here, this alpha right now is at 45. So that tells me that this is a 90-degree angle right here for this cone. Does that make sense? Okay. We can change that. It doesn't really matter. Eventually it's going to get my cones to disappear, but just kind of changes the kind of the breadth of that cone. So right now, if I've got this thing to be 90, if beta is 90, what type of cross-section do you end up getting there? You get a circle, okay? And we talked about that cross-section. Now, no matter where I move this plane throughout those two cones, that's the cross-section that's going to happen, right? Okay? And we talked about circles at the first week of this course, and we should know the formula for any circle, okay? And we'll talk about that here in a little bit again. But now as I start to change the angle of that plane, so now I change that angle so it looks like this, okay? So in this situation, my beta, okay, beta is greater than my alpha. Beta is greater than my alpha, okay? So 50 and alpha is 30. And you see now that cross-section is what type of shape? We want to say oval, right? And you're going to hear me accidentally say oval a lot. But mathematically, oval is not a word. Ellipse, okay? So we've got our ellipse over here, which our ellipse essentially looks just like a circle, but in this case, it's been stretched up and down, right? It's like you grab the top and bottom of your circle and you pulled it apart, correct? All right? That's all that an ellipse is, okay? So what we know about circles is going to help you a lot with how we deal with ellipses, okay? Because they're very similar to one another, okay? Now, if we kind of mess around with stuff a little bit more, okay, so here you're seeing now that that beta angle is less than alpha angle. Do you guys know what that shape is referred to as? That's a hyperbola, okay? That cross-section is a hyperbola. Things that are hyperbolic are useful a lot in physics. Like I said, we talked about, I mentioned telescopes, lenses on telescopes. Usually hyperbolic, trying to kind of get light to focus on a particular location. Now, we can also do this to where these two things are the same. So let's say that alpha is 55. Let's say that beta is 55. Okay, so now you see that the plane essentially is parallel with the lateral, we call that slant height, I guess, back in geometry. That the plane is parallel with your slant height, and what shape does that give you for a cross section? Parabola. Okay, so that's where those things come from. Those four cross sections: parabolas, circles, ellipses, and hyperbolas. We've already talked a lot about circles, so we're not going to talk about those again today or this week. We've already talked a lot about parabolas, so I'm going to scrap that, and we're not going to talk about parabolas either. Okay, ellipses and hyperbolas. Hopefully, knock those out today and tomorrow. Okay. So an ellipse, by definition, okay, says an ellipse is an oval curve that looks like an elongated circle. Okay. Now, like I said, we don't use the word oval; we use the word ellipse. Okay. But here's the geometric definition. It says an ellipse is the set of all points. Sometimes, instead of saying the set of all points, they might write the locus of all points. It means the same thing. Okay, just a terminology thing that you might see and like, what are they talking about locus for? Okay, it's just another way of saying the set of all things. Okay, but it's the set of all points in the plane in which the sum of those distances from two fixed points F1 and F2 is constant. Okay, so that's the geometric definition. I'll show you what that means. This picture's good, but it's not great. What they're basically saying here is that you've got these 2 points, P, let's call this point here P sub 1. If I take point P, you see those two blue distances, right? From F1 to P and F2 to P. If I take those two distances and add those together, that sum is going to be the exact same number as if I take F1 to P1 and add that to F2 to P2. Does that make sense? Okay, so the black distance is here. If I add the black distances together, that should be the same exact sum as the blue ones. If I take those red distances, F1 to P2 and F2 to P2, and I add those together, it's the same number as the blue sum as the black sum. Okay? And no matter where that point P moves around on that that ellipse, okay, that sum of those two segments is always going to be the same. Now, two individual segments will be different, but the sums will always be the same. And when we see that maybe a little bit better with this example, okay? So I can move these foci around. Now, I've got some limitations because of the construction, so I just want to move these around to where, I think that's pretty good, where it shows those two segments, okay? So C is referring back to the point P on the last picture, okay? That's going to be a point that is on the ellipse. And you see then, right now that we're saying C to F1 in the upper left-hand corner says it's 6.74 units long. C to F2 is 22.5 units long, right? Okay. Below that, I've just got to add in those two numbers together and give me 29.24. Okay. So GeoGebra uses the distance formula, and as I hit play here, we're going to see that those numbers start changing, right? These two numbers now are different than what we started with, correct? But when I add them together, is that different than what we started with? No. And I can hit play again. Okay, now those two numbers are different, but is that sum different? No. Okay, so we're maintaining the idea. I'll slow us down over here because of the construction. The points just get closer and closer. The distance between them gets closer and closer, so it slows down. But as we move around, okay, those two distances, call them I and J right now. Those distances I and J are changing, and we see that right here. Okay, they're consistently changing, but the sum of I and J is constant. And that's what the geometric definition said for an ellipse. In order for an ellipse to be created, that has to be true. Okay. Now, where could I use this? Maybe if you've ever watched, PBS? You got like woodworking shows on PBS. You got This Old House. You guys ever watch that stuff? Parents ever watch that stuff? Yeah. Okay. So you got woodworkers on that show, and a lot of times they're like This Old Houses in like New England, restoring old Cape Cod houses and stuff like that. And they want fine, detailed woodwork, and maybe they got to cut out an oval, okay? And a lot of machines maybe can't do that. Cutting out a circle or square, that's easy to do. But an oval, what you end up doing is you take your piece of wood, okay? Maybe my piece of wood is that block right there, okay? I want to cut an oval out of it. So what we do is we take a nail or a pin or whatever, and we put a pin there and a pin there, okay? And that dictates then essentially the size of our oval, okay, or ellipse, I guess, sorry. And then we take a piece of string, and we take that string, we come down, we wrap it around a marker or a pencil, somehow, some tool that's going to trace out our ellipse. And then I take that other piece, other end of my string, and I go down here, and I tie it around that nail. And now as long as I can keep that, those two segments of the string taut, okay, keep them tight so that they don't have any slack in them, and I can move my pencil around, always keeping those two strings taut, I will create a perfect ellipse. Does that make sense? And then I can take my jigsaw or whatever and cut around that, and I have my ellipse, I have my oval that the carpenter wanted. Does that kind of make sense? Okay. So that's the construction of ellipse, the definition of ellipse. Now I want to talk about how that relates to something else that we already know a lot about. Something you guys know a lot about from the first week of school. X squared plus y squared equals, let's say, 100. Let's go smaller. Let's go 64. Gives you that circle, right? Okay. Can I do anything that I want to those three parts of that equation and still get the same thing? For instance, can I take x squared and divide it by 64? Well, I don't want to hit enter. Can I take x squared, divide it by 64? Can I take y squared, divide it by 64, and then take 64 and divide it by 64? Gives me 1, right? Do I get the exact same image? Does that make sense to everybody? Okay. So, now I'm going to put this, I don't know why it changed it to that form. I want it back to that form. So right there we're seeing that x squared plus y squared equals 64 is the exact same thing as x squared is 64 plus y squared is 64 equals 1. A lot of times when we deal with conic sections, we want that number on the right-hand side to be a 1. Okay? Because of some algebra that we go through to recognize the actual equation or the general format for circles and ellipses. We want that number to be a 1. So in this case, we've got it to be a 1. That's the format of a circle. Well, how do we make a circle into an ellipse? We talked about how we just grab the sides of it and pull apart, right? If I take your hand at like -8 and +8 on the x-axis, grab that circle and move your hands outward. Will that create an ellipse? Okay. So if I pull, let's say, try to pull this one out to -10, this one out to 10, it's going to elongate that circle horizontally, and then it's going to kind of bring these two distances down. Okay, and it'll give me my ellipse. How do we do that? Okay, if I had a number like 3 there and a 3 there, still gives me a circle, right? Maybe, so just showing you that I still get a circle here, with that being a 3 and that being a 3, I get the exact same circle again. Okay, so changing the coefficients changes the circle, but it doesn't change the stretch of it. Okay, the horizontal stretch or the vertical stretch. But what does happen is that if these coefficients are different, that was a 1 and that one's a 3, right? So this would be 1 over 64, and this would be 3 over 64, and now we get our ellipse. Okay? Does that make sense? If you guys remember from last year, a lot of these shapes, when we talk about ellipses and hyperbolas, their algebraic format is very similar. One has a plus sign in it, one of them has a minus sign in it, right? The way I remember it is that ellipses and circles are very similar, right? We know, it's just second nature, the equation of a circle by now. We've seen it so many times. And it has a plus sign in it, right? So an ellipse is just like a circle, so it's got to have a plus sign in it. And that's what kind of that demonstration is trying to show you, okay? Generally speaking, and I'm going to put a video together that walks you through this derivation. I think it's a good algebra activity to see and go through, because it is algebra you guys can do, that you can walk through. It's geometry, basically, to set up the equation, and a little bit of algebra, too, to go through and evaluate it. But eventually, it gets you down to that format right there. And that is the general format for any ellipse that we're ever going to come across. Okay? Now, if you remember last year, you were probably presented a table of facts that said, pay attention to how big A is compared to B. And pay attention whether A is with X or A is with Y. And then that changed kind of the look of your ellipse. Okay? I'm not going to ask you to do it. I think that's cluttering your mind. Okay? And it's going to make you make mistakes. Okay? I don't care what A is. I don't care what B is. I don't care that A goes with X. I don't care that B goes with Y in this case, because they could flip-flop, they could change. All I want you to know, and you already know how to do this, when I look at A squared and that becomes a number, let's say A squared is 16 and B squared is 36. Can you tell me which one's bigger? Can you tell which bigger, 16 or 36? 36, right? So whatever denominator is bigger tells you then what axis is bigger. Okay? Because if 36 is stuck with the y, that tells me my y-axis is bigger. That becomes what we call our major axis. If the a squared number is bigger, then the x-axis, or my horizontal axis, is bigger, and that's our major axis. Does that make sense? Okay? Don't worry, and I'm going to show you maybe what you saw last year, or something similar to what you saw last year, like this. There's a lot of stuff there to remember, and a lot of stuff there to, if you memorize it, for the potential of you making mistakes, right? Okay? Because there's two situations. It's when your ellipse can be elongated horizontally, or it can be elongated vertically. Okay? So that's where those two columns come from. And that's all dependent on A and B, which one's bigger and which one's smaller. I'm not going to ask you to do that. I think the work that we go through is going to be pretty explicit in telling us which one is going to be our major axis in disregard to this A and B stuff. What I do think you guys should make note of is that formula right there. Okay? It's going to tell you your focus length. Okay? C squared equals A squared minus B squared. I remember the word cab. Okay, and that's going to help you with this and hyperbolas. But with this one, you've got subtraction. Okay, so the A and the B are getting subtracted. And that's going to tell you the distance that your focus is away from, in this case, your center of your ellipse, which is right now located at 0, 0. So I find that, I take square root of both sides, and I find that distance for my focus. Okay? That's where we put those two pins. And if we were doing that, try and trace out that ellipse on that piece of wood. With hyperbolas, that's going to be a plus sign. Okay? The one thing that I kind of mess around with, and I know the word cab, sometimes I get the plus and the minus messed up. If I go through this word, and maybe I accidentally put a plus sign there, it's probably going to put my foci on the outside of my ellipse, and that's a problem. So I know then that formula was wrong, and then I need to change the plus sign to a minus sign, and that will put my foci on the inside. Does that make sense, everybody? Okay. Maybe see an example here in a little bit that can kind of show you that situation. All right, so get an example here, and we're only going to get through one example, which I know is not ideal, but I will put together a series of examples in a video, either today or tomorrow, post online so you guys can push through the assignment. All right, so it says find the foci of the ellipse and sketch its graph. First thing I'm going to do before I find the foci is I'm going to sketch the graph. Because then that reminds me of whether I've got the foci in the right spot or not. And I use the right equation. So, this is a lot of times referred to maybe like the, I think in circle form, I would call that standard form. Basically what we want is we want to be able to rewrite this so that the 144 is a 1. We always want 1 on the right-hand side. So the way we do that is we just go through, divide everything by that constant. Make it that. And then yours just simplify. 16 and 140, and a lot of times when they write these, they've got this in mind as they're writing these for you in your homework. I'm going to say every time, but a lot of times, 16 and 144 are going to have a common factor. And that's, in this case, going to be 9. So I get something like that. And now we put this thing in kind of that ellipse form, okay, that geometric form. Now I'm going to graph it, so all we have to do is set our x and y axes up, and you look at your denominators. Okay, now this number right there, I don't care which one it is, but it's either a squared or it's b squared. Okay, so what I want you to know is that that is not just a, it's a squared. Does that make sense? We want to kind of set the endpoints of our axes, the endpoints of our ellipse on the x-axis and the y-axis. So the way we do that is we take that number and you take the square root of it. So it's square root of 9. 3. And now because that number was attached to x, I'm going to now plot on the x-axis that distance of 3. I'm going to go 1, 2, 3, and I put a point there. 1, 2, 3, and I put a point there. Because when I take square root of 9, I get plus or minus 3, don't I? Okay. So taking the square roots of your denominators is going to tell you where the endpoints of your axes are. Now, which axes? Well, it depends on what, that denominator was stuck to the x, so that's the horizontal axis. So I go up 3 units in both directions on the horizontal axis. This one's stuck to the y. Okay, so I'm going to go out how many units on the y-axis? I'm going to go 4 units on the y-axis. Take square root of 16 gives you 4. So I'm going to go 1, 2, 3, 4. Put a point. 1, 2, 3, 4. Put a point. And now I've got the enough points. Usually we want to use those to kind of define our ellipse. All right. I'm terrible at drawing ellipses. You're probably going to be pretty bad at them too. A lot of times especially when we make our own axes and set up our own intervals, a lot of times they don't maybe look perfectly elliptical. But that's what we've got going on. Okay. Now I want to find the foci. Okay? So the foci, remember, is the word cap. And they're always squared. Okay? Now, I know it's subtraction. Okay? But let's think about it. If I put addition in here, what's 9 plus 16? 25. What's square root of 25? 5, right? Would that put me on either axis outside my ellipse? So I know it can't be plus inside that formula. It's got to be minus. Now this is giving me a distance, right? Distances always have to be what kind of number? Positive. Okay? So how do I have to orientate these so I get a positive number? 16 minus 9. And that's really why, back in that blue chart on slide 15, you see two columns. And they talk about what A is bigger than B and B is bigger than A. It's because of how we have to do subtraction here. But we all know how to do subtraction to get positive numbers, right? The bigger number has to come first. Okay? So now I get C to be root 7, which I believe that's about 2.64, I think. Okay? And if you remember from last year, your foci are always on what axis? The major axis. They always go on the bigger one. So right now our major axis is the y-axis, right? So I'm going to go 1, 2.6, 1, 2.6, and that's F1 and F2. And again, it doesn't matter which one's F1, F2. Those are my locations and my focus. Okay. Is that something we can do? I will put together a couple videos of examples that are similar to what you see in your homework. But that homework assignment's not due until Monday.